The objective of this video is to describe the difference between mass number and atomic mass. Mass number and atomic mass does not mean the same thing. They mean two different things. We sometimes use other names like the average atomic mass or the relative atomic mass. All these three names, atomic mass, average atomic mass, or relative atomic mass, all three of them mean the same thing, atomic mass. However, keep in mind that atomic mass is different from mass number. In order to explain the difference between atomic mass and mass number, I'm going to take two atoms. The first atom, you find 5 protons and 5 neutrons. In the second atom, you find 5 protons and 6 neutrons. We define mass number as the sum of protons and neutrons. Mass number is usually symbolized by capital A. So the mass number is the total number of protons plus the total number of neutrons. Using this expression, we can calculate the mass number for the first atom, which is 5 plus 5. We get the mass number 10. For the second atom, 5 plus 6, we get the mass number 11. By now, you are aware that the relative mass of one proton is 1 AMU, atomic mass units, and the relative mass of one neutron is 1 AMU. So using this piece of information, now we can rewrite this mass number in terms of AMU. There's 5 AMU here and another 5 AMU here. So this 10 can be written as 10 AMU. Similarly, we can write the 11 as 11 AMU. You know that in atoms, you have protons and neutrons in whole numbers. You don't find a fraction of a proton or a fraction of a neutron. So this mass number is always going to be a whole number. Now in these two atoms, you find 5 protons in both atoms, but different number of neutrons. What does that mean? If you have the same number of protons and different number of neutrons, that means what we are looking at is isotopes of the same element, because the number of protons gives us the atomic number. Both atoms have the atomic number 5. So let's go to the periodic table and look at the element which has the atomic number 5. That is boron. So that means these two atoms I have shown here are isotopes of boron. Now in this information you see here, you can see this number 10.801. So what is this? The mass number of one isotope is 10 and the mass number of the other isotope is 11. And the value we see from the periodic table is somewhere in between. So this is the figure we actually name as the atomic mass. So that means now you know what you see here in the periodic table is not the mass number, that is the atomic mass, which we also call as the relative mass or the average mass. Now let's see how we can calculate the average mass. Here I'm showing you the same two atoms I have shown you earlier, the two isotopes of boron. The first one is boron 10. You can see that this 10 relates to the mass number. So if we show a number with the element, that number tells you about the mass number. And then this atom, this is boron 11. You can see this 11 represent this 11. Now you know how to calculate an average if you're given two numbers. Let's say if you're given the number 10 and 11, asked to calculate the average of 10 and 11. The regular way you would calculate the average is you add 10 and 11, divide it by 2, you get this figure, which is 10.5. However, when we check the periodic table, we still don't have this number. So that means the method we use to calculate the average is wrong. That means the regular technique we use to calculate average does not work when we try to calculate the average atomic mass. Then how can we calculate the average atomic mass? Now I'm going to show you why we have to use a different method to calculate the average atomic mass. Think you are provided a sample of boron. This sample is made of boron atoms. Some of these atoms are from boron 11 isotope and the others are going to be from boron 10 isotope. That means this sample is a mixture of boron 11 and 10 isotopes. If we think about all the boron atoms on this earth, only 20% of those boron atoms are going to be from boron 10 isotope and the remaining 80% is from boron 11 isotope. Now this pie chart shows you the natural abundance of these two boron isotopes. This difference in the natural abundance is the reason why we cannot calculate the average atomic mass the regular way we calculate an average. If this abundance was 50-50, if both isotopes were present in 50-50 percentages, only then we could have added these two numbers and divided it by 2. Since they are not 50-50, we have to use a different method. In this different method, we use the mass number and the natural abundance to calculate the average atomic mass. So in this formula, we first mention the mass number of the first isotope and then multiply it by its natural abundance as a fractional value. To that, add the second isotope. We have the mass number of the second isotope multiplied by its natural abundance. Now this part you can see it relates to boron 11. We have 11 here, that is the mass number, and this 80.10, that is the abundance as a fractional value. You can see this 100 as the denominator, so you have to write it like this. To that, add the next isotope, which is boron 10. You can see that 10 over here, the mass number, and then the natural abundance as a fractional value. Now this number we have obtained match with what we see from the periodic table. And also you can see that this value 10.8, this value is a little bit closer to 11 than 10, and that match with this abundance. Why? Because we have 80% of boron 11. So that is why we do not end with 10.5. This is 10.8 because we have more of boron 11 and less of boron 10. As a summary, mass number means the sum of protons and neutrons, and this is always a whole number. And the atomic mass or average atomic mass or relative atomic mass is the value calculated using mass number and the natural abundance.